second chapter deals with chemistry. And chemistry is important to us because we're going to be talking about a lot of the atoms and a lot of the molecules that make up our body that we take in through the foods that we eat and put them together in different forms to build all the parts of our body. Okay, so we don't have to know a lot of chemistry for anatomy and physiology, but we do have to understand how these atoms and molecules behave and the arrangement of these in specific molecules. Okay, so let's get on. We always start out with a discussion of matter. Matter is anything that has weight and takes up space. So that's going to include our solids, liquids, and gases. So as you know, if you inflate your tire or your basketball or whatever, we are adding more air into it. Well, that air is composed of atoms of elements, okay? And that actually causes that tire or that basketball to weigh more because we've put more of these molecules, these atoms into the tire or the ball, okay? So matter is anything that has weight takes up space. 3 different forms it can exist in: solids, liquids, and gases. And it's going to be, this matter is composed of the different elements. Now we've got 112 or so known elements, and we know them by names like iron, copper, silver, aluminum, things like that. The good thing for us is the living organisms, we only really require about 20 of these different elements, okay? 20 different elements. And the big 4 for us are going to be oxygen, carbon, hydrogen, and nitrogen. And those 4 elements make up more than 95% of our body. So we're going to spend a lot of time talking about oxygen, carbon dioxide, hydrogen, and nitrogen, and putting them into different molecules in order for us to create the structures that we need in our body. Okay, so an atom is the structure that these elements are in. Okay, so there's lots of different atoms of these elements. Okay, so the elements are composed of tiny particles that we call atoms. So that's going to be the structure that they're all going to resemble. Okay, these are the smallest complete units of the element, and they vary based on these elements. Their size changes, their weight changes, how they interact changes, the number of particles that they have changes. Okay, so when we think about the atom, they are composed of protons, neutrons, and electrons. Okay, so a proton, that is a positively charged particle, and we find it in the nucleus. This is where we also find neutrons. Okay, these are the neutrally charged particles. They're inside the nucleus of our atom. And then the electrons, they are circling the nucleus in a specific orbit, much like the planets do. Okay, they're circling this nucleus and they have a negative charge. So we end up with a positive charge, a neutral charge, and a negative charge. Okay, and one of the rules that we learn in chemistry is that the atomic number is of this element. Okay, the atomic number is just how many protons we have. Okay, and for us, that number of protons, okay, should equal the number of electrons to keep everybody even. Okay, so when I think about it, I always think about if they tell me the number of protons, I can come up with the number of electrons. Okay, and if you have the same number of protons, you belong to the same element. Okay, and that's one of the things that we have kind of a constant in chemistry is we really can't change the structure of these very much. Okay, so atoms with the same number of protons, or we could say it as the same atomic number. Okay, they are the same element. Okay, so this shows you a couple of examples. Here's hydrogen, and hydrogen has 1 proton. It has 1 proton, it's going to have 1 electron. And notice that 1 electron is orbiting out in space. We can see it out here going around the nucleus. Here's where our proton is. This is where the positive charge is. This is where that negative charge is. Okay, and this is the way it's going to set up. So it works fine for our organization of this atom. Now notice it doesn't have any neutrons. This is the only atom that doesn't have neutrons is a hydrogen atom. Okay, now let's look at oxygen. Okay, so with oxygen, we've got 8 protons. So I can find 8 protons in here. And it says it has 8 neutrons. So I can find other 8 in there. So that should give me 16 little particles in here. And if I've got 8 protons, we know we've got 8 electrons. And that's these little guys out here that are circling the nucleus. Okay. Now, while we're here, there is a specific arrangement that these electrons can have. Okay. In the first orbit closest to the nucleus, this one right here, you can only have up to 2 electrons. Okay. And then in this orbit, the maximum that you can have is 8. Okay. And that's going to be important to us coming up. So I wanted to go ahead and show that to you now. So we kind of put that in the back of your head as we're going through this. Okay. So now I said the maximum it can have is 8. With this one, oxygen has 1, 2, 3, 4, 5, 6. So it could have 2 more. Okay. You can have 2 more electrons, but in this case, okay, it just has 6. Okay, let's get the atomic weight of something. Okay, so mass is how much of it do you have. Weight is what does it weigh in the presence of gravity. Okay, so think about this. I would weigh a specific amount here on Earth, and if I went to the moon, I would weigh less, right? My weight would be less. Well, the reason for that is because gravity is not exerting the same amount of pressure on us, okay? But my mass stays the same. I still have the same number of particles in me, okay, as I did when I was on Earth. So mass says how much of it you have. Weight is in the presence of gravity. So the good thing for us is we're going to stay on the planet Earth, so that's going to help us out a lot, okay? This atomic mass is the sum, since it's mass, we're referring to how much of it do we have, okay? The sum of the masses of our protons and our neutrons. So when we look at a proton and a neutron, they're going to have a specific mass, and it's equal, okay? We're going to say that they're both the same size, and we're going to call it this mass unit, okay? They're equal to 1 mass unit. Now notice that the electron is much, much smaller, okay? It's like 1/1840th of the size of a proton or a neutron. So for us, that's going to be negligible. We're not going to worry too much about how much an electron weighs, okay? So the nice thing for us is we can add up the number of protons and the neutrons, and it's going to give us the atomic mass, okay? So all the atomic mass is the sum of the masses of the protons and neutrons. How many protons you got, how many neutrons you got, and that'll tell us what the atomic mass is, okay? Now, we can change the number of neutrons inside the nucleus. That's changeable. Protons are not, okay? Neutrons we can. And if you go into radiology, there's several students that take anatomy and physiology that want to be radiology techs and that kind of stuff. You end up dealing with these isotopes of elements because they have they have more neutrons, and that makes them radioactive, which we can trace in the body. Then they give off radiation that allows us to track them in the body. Okay, so notice that down here we have 3 different forms of carbon. It all says carbon, carbon, carbon. And notice they all have 6 protons, so we know it's carbon. 6 protons, that's the number for carbon. We got 6 electrons, that's how many carbon has. And then the number of neutrons, though, look, can change the number of neutrons. That just makes carbon-14 a little bit heavier, makes carbon-13 a little bit less heavy, and carbon-12, this is the one that is our lightest form. Okay, this is the normal one that we find in nature. And then we find these radioactive forms as well. We don't find a lot of them, so most of what we deal with is carbon-12. But we can do carbon dating, and that reflects how these radioactive forms return back to their original state of carbon-12. Okay? So they're going to spontaneously decay. Okay, and we'll come back to some of these isotopes here. But all an isotope is, you got more neutrons. Okay? But this is what we would think about when we think about carbon. It's got 6 protons. Okay, I can look up on a table, and if it's got 6 protons, it has the atomic number 6. I know it is carbon. Okay, it even tells me it's carbon. Okay, and we can change the number of electrons. Okay, but we can't change the number of protons. If we have an atom that has a different number of protons than electrons, okay, we say it is an ion. Okay, it is an ion. It has a different charge. It has a charge on it then. Okay, if it has more protons than electrons, it's going to have a positive charge. If it has more electrons than protons, it's going to have a negative charge. That's right. Okay, so the number of electrons we can adjust, okay, based on making this element or this atom of an element happy. And I'll explain how we can make it happy coming up. Okay, so if you have a different number of neutrons, we say it's an isotope. If you have a different number of electrons than you do protons, we say it's an ion. Okay, and there's 2 different ways we can talk about it. If you are positively charged, if the atom is positively charged, we say that ion is a cation. If it is negatively charged, if it has more electrons than it has protons, we say it is an anion. So cation and anion are the terms that we use to specify the charge on this ion. Okay, so like I said, electrons are going around the outside of the nucleus of our atom. Okay, and the chemical behavior is going to be based on how many electrons you got. And we know how many electrons you got when we start with this, because that should equal the number of protons. And the atomic number tells us how many protons we have. So we look all this up, makes it easy for us. Okay, so look here, we've got oxygen, 8 protons, 8 neutrons, 8 electrons. Okay, number of protons equal the number of electrons. Okay, and it says these electrons are attracted, because they have a negative charge, they are attracted to the nucleus. Why are they attracted to it? Because in nature, opposites attract. Okay, positively charged is attracted to a negatively charged. Okay, and we're going to see this all throughout our bodies. Okay, we're going to put positively charged things with negatively charged things. Okay, so these electrons, they're negatively charged. The protons that are inside the nucleus, they're positively charged, so they are attracted to one another. So normally they would come together, okay, because they're attracted like a magnet. It would suck them together, okay. But there's something in this atom that keeps the electrons out there, okay. It holds them in their position, and that is the energy that that atom possesses. Atoms have energy. We call it the potential energy of position, okay. It's the energy that that atom possesses. Okay, now the closer you are, the less energy it requires, right? Because it's not a lot. But the farther away, it takes more energy to hold those where they're at, because they're farther away. Okay, so we'll talk about that coming up very shortly. Okay, so this shows us in that first energy level, it's showing us the K energy level. We can have how many electrons? We can have 2 electrons in this one, okay? And the next one, we can have 8 in the L, and in the M, we can have 8. And as long as we can count to 8, we can do chemistry in anatomy and physiology. Okay, so 2 in the first shell, okay, 8 in the second shell, L, 8 in the third shell, okay? And this is how we use these atoms to hold on to energy for us, okay? If we let the electron fall down from a outer orbit, if we move it to this orbit, we release energy. We absorb energy if we go this way. If we kick it out to a higher orbit, because it would take more energy to hold it out here, right? So we have to have an increase in energy. So let's take a photosynthetic plant, okay? What happens when the sun hits that atom is it causes the electrons of that atom, when we're doing photosynthesis, the electrons jump out here, and that gives us more energy. That atom has acquired the energy, and all we have to do, we call that the light reaction when this happens. And then the dark reaction, when it falls back down into place and we're able to release this energy, that's the energy we use to put together the glucose molecule from carbon dioxide and water. And that's what we call photosynthesis. That's where the energy comes from exciting electrons and then allowing them to drop back into their normal position, releasing the energy, and we can use that energy. Or plants can. I wish we could, but plants can. Okay? Okay. So this is an arrangement of a bunch of elements that we can see here. We're going to have a periodic table coming up, and this is kind of what we've taken from the periodic table. But we can look at a lot of different atoms here of the elements, and we can arrange them based on the number of protons they have, because the number of protons is going to equal the number of electrons, right? So let's take a look. Get a pin out here. Here's hydrogen. Hydrogen has an atomic number of 1 because it has 1 proton. If it has 1 proton, it has 1 electron. Okay? And then let's move down here to where lithium is. Lithium has an atomic number of 3 because it has 3 protons and 3 electrons. Okay? Here's carbon. Carbon has a atomic number of 6 because it has 6 protons. There's the positively charged 6 in the middle, and then the negatively charged electrons you can see on the outside. Okay. Then we see oxygen here, 8. Okay. We've got neon over here. It has 10. It has 2 in its first shell, and it has 8 out here in its outer shell. So this one's completely full. Remember, you can only have 2 electrons max in the first shell and 8 electrons out here in the second shell, as well as the third shell can have 8. But this one, and you always fill, I should say this too, you always fill it from the inside to the outside. So you got to put the 2 in first before you can start adding to the next one. Okay, and you got to fill that shell, and then you can move to the next one. Okay, so we say that if you are completely full, okay, you're happy. And what I mean by happy is you don't react with things. You don't need anybody giving you anything else. You've got all the electrons that you need. Okay? So if we have just 2 in the first shell, okay, we call that helium. Okay? Helium is He. It's got 2 protons, and then circling around the outside of it, it's got an electron here and an electron here, just 2. Okay? Helium's happy. Okay? Neon's happy. Why is neon happy? It's got 2 in the first shell, and how many in the second shell? It's got 8. It's full. Okay? Then look down here. Here's argon. We got 18. 2 in the first shell, 8 in the second shell. That makes 10. 8 in the third shell. That makes 18. Argon is happy. Okay? And these guys, if you are happy, you do not react with anybody else. Okay? You are just helium. You'll never hear helium chloride or helium oxygenate or anything like that. They don't make molecules. They exist by themselves. Okay? Same thing with neon. Neon carbonate. No, you don't hear that. It's just neon. The neon lights of Broadway. Okay? Those kind of things. Argon, same thing. You don't hear argon attached to anything else, because they're full. And these are the only ones that have that full outer shell. Everybody else then, all of these don't. So what does that mean to you? If they don't have a full shell, they are reactive. These are the ones that we're going to be able to do chemistry with. Okay? We're going to be able to do chemistry with these. And the goal simply becomes fill the shell. Figure out a way to get the shell full with electrons. Okay? Get it full. Now remember, it's going to have a specific number of protons inside the nucleus. That can't change. So the inherent characteristics of that element is preserved. Meaning, even if I get an electron or I give away an electron, I'm still whatever I started out as. Okay? For instance, let's look at this one right here. Here's lithium. Okay, this is lithium. How many electrons does it have? It has 3 electrons. How can we make lithium happy? Okay, we got 2 choices. We can either give away this electron, and that means we would have 2, and then it would be happy because it would have a full shell. Okay, we can either give away this one, or we can add 7 electrons to it to make it happy. That would give it 8, and it would be happy, just like neon then. Okay, now which seems easier? Give away an electron or find 7? Okay, and you're right. The answer is always we take the simplest way, always. Okay, so it would be easier to give it away. If we give it away, change the number of electrons and protons. Now we have made lithium an ion. We've given away the electron. We've given away negativity. So it's going to become positive. There's going to be 3 protons on the inside, but only 2 electrons. Because we gave 1 electrons away, that makes it a positive ion. Okay? That would be a cation. Okay? Let's look over here at oxygen. Okay? Here's oxygen here. Oxygen has 8. 2 in the first shell, but only 6 in the second shell. What does it need to be happy? We got to give away 6, or we got to find 2. Okay? We got to find 2. So, let's do something that y'all know real well. Y'all know water, H2O. Okay? So oxygen needs 2 to be happy. Could we use the 2 electrons here to join with this, okay, and make it happy? Absolutely. So 2 hydrogens plus oxygen, that's water, okay, makes everybody happy. So we're able to utilize this system to make it happy. There's different ways that we can do it. We can put these electrons together differently. But the goal has to be make everybody happy. Okay? So, here's sodium. And sodium is part of salt. Okay? Sodium is part of salt. Sodium chloride. Let's look out here. Sodium has 1 extra electron. Okay? If it gives away its an electron, it's going to be happy. And what charge would it have? You gave away an electron, so it has more protons than it has electrons. So it'd have a positive charge. It would have a positive charge. And that's what we see happens when I take in salt. I take in salt. It ionizes and becomes sodium with a plus charge on it. Okay? All we're doing is messing with the number of electrons. Okay? All we're doing is making sure that our electrons end up equaling whatever the total of that last shell can have. Okay? Be it 2 or be it 8. Okay? As long as we can remember those, we can do this. Okay? So, this shows you if I give away an electron, okay, the term we use to say that is we have become oxidized. Okay? When we do these chemical reactions, and that's really what we're doing when we give away these electrons and we accept these electrons, is we're doing chemical reactions. Okay? Electrons are going to be transferred. We're going to give them away. Okay? We're going to accept them. Okay? So we say that oxidation is the loss of an electron. Okay? And reduction is the gain of electron. And that doesn't seem, if you're reduction, why would you be gaining electron? Well, remember the electron is negatively charged. Okay, so you're not gaining a charge with this. Okay, you're gaining the electron, so we call it reduction. And I always think about it like this: if I got a speeding ticket, it's going to negatively affect my bank account. I'm going to have a reduced amount of money in my bank account when I pay for this. But if I give you the ticket now, your bank account's going to be reduced if you're going to pay the ticket for me. And I appreciate you paying the ticket for me. Okay. Okay. So we said 112 known elements. Okay. We got a few of these, or most of these occur naturally. We've been able to make several of these in the lab, but most of these occur naturally. And there was a Russian chemist way back in the day that came up with a periodic table. And what he did was organize all of the elements that they knew at the time into a table to make it very easy for us to identify what's going on. Okay? We're going to follow this octet rule, which says the atoms that are important to life, okay, can contain no more than 8 electrons in that outer shell. Okay, 8 electrons in that outer shell. If they are filled, if the outer shell is filled, we say they are inert, meaning they will not react. Okay, and the ones that react are the ones that don't have their outer shell full. Okay, so let's look at the, okay, here's our periodic table, and the number that you see in the top left corner, okay, that is our atomic number. So this tells us I've got 1 proton over here. With helium, I've got 2, then lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluoride 9, neon 10, sodium 11, magnesium 12, aluminum over here, silica, phosphorus, and it goes on. Okay? So this tells us the number of protons, and if we know the number of protons, we said we know the number of electrons, right? Because the number of protons, starting out when we're thinking about it for chemistry, it's going to equal the number. Protons equal the number of electrons. Okay, so I mean if electrons are wrong. Okay, and the nice thing is we've organized this so that if you look over here in this column, okay, this one says I've got 2, and 2 is a full shell, right? 2 in the first shell. And then 2 plus 8, that's a full shell. 2 plus 8 plus 8, that's a full shell. Okay? 2 plus 8 plus 8 plus 8 plus 8, it keeps on going. We get all of these that you find here. These are all called the noble gases. These are the ones that do not react with anybody. Okay? They're all happy. They're going to do their own thing. Okay? But what that means is everybody else from this column to this column and all the way down, okay, including these guys, these are all going to react. Okay, these are all going to be reactive. Okay, but again, we said that most of the body is made up of 4 different elements. We've got hydrogen, we said, we've got oxygen, we've got carbon, and we've got nitrogen. Okay, those are the 4 biggies. Okay, and those, the highest number for that is only 8. Okay, we got 1, we've got 6, 7, and 8. So really, we don't have to count a whole lot when we're dealing with a lot of the atoms that we're messing with in the body. Okay, so this is that setup. And look at the amount of each one of the elements in the body. Okay, we are 65% oxygen, carbon 18, hydrogen 9. Okay, nitrogen 3, and then it gets very small after that. Okay, so, and then the body, we've got some trace chemicals that you can see over here on the right hand side, like zinc, okay, like aluminum. There's even a little bit of gold in the body, and then kind of stuff. So not enough to kill anybody, but just a little bit. Okay. So the way we're going to hook these together is by using chemical bonds. Okay. And we're doing chemistry now. We're putting things together. Okay. So chemical bonds, when we think about it, a molecule refers to groups of atoms held together by energy. Remember that those atoms have energy in a stable association. Okay, if we use different kinds of atoms, we say it's a compound. Okay, molecule like oxygen to a group of atoms held together, but if we use different kinds of atoms, different elements, okay, we call it a compound. And what we're going to be using is a type of energy, okay, to make these bonds. And we've got three types of chemical bonds that we're going to learn. We're going to learn an ionic bond, we're going to learn the covalent bond, and we're going to learn the hydrogen bond. Okay? Okay, so the first chemical bond that we're going to talk about is an ionic bond. And ionic bonds are easy because the first three letters of ionic is ion. So we're going to use ions. And we know how ions are formed in that in order to get happy, they had to give away an electron or accept an electron. And this is what happens with sodium and chloride. Okay? So notice here, sodium has an extra electron. It wants to give one away. And chloride, it needs one electron to be happy. Okay? It has 7 in its outer shell. So the one that sodium has, if sodium can get rid of one and chloride could accept that one, they would both be happy. But look at what happens when this happens. Okay? When the electron is given away from the sodium, it becomes a positive ion, a cation. The chloride accepts that electron, becomes an anion, and now the sodium has a positive charge on it, and the chloride has a negative charge on it. Do positive and negative things, are they attracted to one another? Absolutely. So we get a bond based on this charge, okay? And that's why we call it an ionic bond, okay? It's because they have opposite charges, okay? Opposite charges that force them to be attracted to one another. And that's why you see this salt crystal over here, okay? The salt crystal. Notice the chloride in the middle is surrounded on all 4 sides by sodium because the positive is attracted to the negative. And then the chloride, notice, okay, it surrounds all of the positive charges. And this is how we form these crystals, okay, a salt crystal. Now what happens when you throw it into water? You throw that salt into water. Well, it ionizes. Water gets between the sodium atom and the chloride atom and forces them apart. And we end up with sodium, an ion of sodium, and an ion of chloride. So they would look like these bottom 2 in water. Okay? And that's what happens if we boil all the water out of our pan after putting salt in it. We're left with salt in the bottom of our pan again because they come back together. Okay? So that's an ionic bond. Then we have a covalent bond. Covalent, we're going to share electrons with a covalent bond. And I always say sharing is caring, and caring starts with a C. So does covalent. So notice that we've got 2 hydrogen atoms in this illustration. And as long as those hydrogen atoms stay in this orientation, they are sharing it. They're both happy. So this one, this electron is going to go around this one. Okay, and sometimes it's going to go around this one. As long as they're in this orientation, okay, we don't know at any point where the electrons are because they're moving so fast, but they are sharing them. It's like they both have 2. Okay, if you share 1 pair, we call it a single covalent bond. If you share 2 pairs of electrons, we call it a double bond. 3 pairs, we call it a triple bond. Okay, and these increase in strength, okay, holding them together based on the number of shared electrons you have, shared pairs. Okay, so that's the second type. Ionic covalent is hydrogen bonding, and hydrogen bonding in our body is going to happen because we are mostly water, and the water molecule has a little bit of a charge on it. Okay, I'm going to show you this coming up again when we talk about water. But when we draw water, there is a big oxygen atom in the middle, and that oxygen atom has two covalently bonded hydrogens to it, and it ends up kind of looking like this, like Mickey. Okay, and they're sharing electrons. Okay, keeping them in this position. Remember, the oxygen has 6 electrons in its outer shell, has a total of 8, and then the hydrogen has the one out here that it can share. Okay, so the oxygen shares one of theirs with the hydrogens. The hydrogens are happy because they have 2. Okay, 1, 2. This one's happy, 1, 2, and this hydrogen or this electron's able to do this sometimes too. So everybody's happy. But here's the deal. Okay, the oxygen's bigger than the hydrogen, so the electrons stay going around the oxygen a little bit longer than they stay going around the hydrogen. That means the electrons are going to spend more time around oxygen than they are going around the hydrogen. That means if you got more electrons over here, it's going to be slightly negative over here, and it's going to be slightly positive over here. That means it's got a charge on it. Okay, and we say it's got polarity. It's polar, meaning it has both charges. It has a positive charge and it has a negative charge on it. Okay, remember the ions just had a single charge on it. This has both. So this means it likes anything with a charge on it. Water likes anything with a charge, and that's why water would get in between our sodium and chloride earlier, because the sodium, water likes the sodium with this part here. Water likes the chloride with this part up here. Okay, so this hydrogen bonding is weak. Okay, it's a weak bond, but depending upon how many molecules you have, okay, it can be a tremendous amount of hydrogen bonding going on. Okay, so it says the oxygen atom is more electronegative than the hydrogens are. So the oxygen is more negative, the hydrogens are more positive, and that causes this polarity to occur. So with our bonding, okay, ionic, covalent, and hydrogen bonding, what we're doing is chemical reactions when we're doing these. Okay, if we break the bonds, okay, if you throw salt into water, you do a chemical reaction. We break bonds. Okay, if you boil the water out and we make bonds, that's a chemical reaction. Okay, so all chemical reactions are is making and breaking bonds. Okay, and we've got certain physical features that will affect these chemical reactions. One is temperature. Temperature affects chemical reactions. It speeds them up. Okay, we also have the concentration of reactants and products. How much do you have? Okay, and a lot of times if we start out with a bunch of reactants, things proceed very quickly, but the more product you produce, it starts slowing down because the product starts getting in the way. And the third thing, a catalyst. Okay, we're going to spend a lot of time talking about catalysts in our body in the form of enzymes. Okay, and enzymes speed up chemical reactions. It's like having a coupon for the energy necessary to do these chemical reactions. I'll talk a lot about enzymes coming up. Okay, so energy. Okay, it's going to in order for us to function, we have to produce energy. Okay, and what is energy? It is the capacity to do work, the power to do work. And all work is a change in mass or distance. Okay, so inside of your body right now, you have energy that we are using. We call that kinetic energy, the energy of motion. You also have potential energy. Okay, we have stored energy that's available for us to reach in and pull out when necessary in order to do a more energetically expensive function. Okay, or to keep going. Okay, so for us, the energy that we're going to talk about the most in our body is chemical energy, and it is in the form of ATP, adenosine triphosphate. That's the that's the gasoline that our car runs on. Okay, it's the ATP is what our body runs on. Okay, and we're also going to talk about electrical energy when we talk about the nervous system and how muscles work. We're going to talk about mechanical energy in the form of moving things with our muscles. And because we generate heat doing these chemical reactions, we're going to talk about radiant energy as well. Okay? Radiant energy as well. But the primary energy source that we use in our bodies, this is ATP. Okay? So in our bodies, we're going to do a bunch of exchange reactions. Okay, what's an exchange reaction? Well, that's when we combine a decomposition reaction with a synthesis reaction. We're going to break things down and we're going to build things up. Okay, so if you had eggs and bacon and toast and that kind of stuff for breakfast, we're going to take those molecules that are found inside of the eggs and the bacon and the toast, and we are going to break them down. Our digestive system is designed to break them down into very small units that we can then absorb and send to the cells. And the cells are going to take these bitty pieces and they're going to make bigger molecules out of them. They're going to synthesize whatever the cell needs. Okay? So we call these exchange reactions because we're going to go decomposition, break it down, then we're going to build it up with the synthesis reaction. And we're going to use water to do this. We can use water to break molecules down. And we can take water away from molecules, harvest that water, and stick things together. If we're using water to break it down, we call it hydrolysis. And I will show you that several times through this course. And then dehydration synthesis, that's where we take the water away and combine two molecules together to form a molecule. Okay? So, when we're doing this, we are going to talk about both organic and inorganic molecules. Okay, with organic molecules, you got to have two different elements involved. You got to have carbon atoms and you got to have hydrogen atoms. If you don't have both of these, it is not an organic molecule. Okay, so it takes carbons and hydrogens together to be an organic molecule. To be an inorganic molecule, you don't have to have a carbon or a hydrogen. Or if you have a carbon, that doesn't make it an organic molecule. Okay, so it's an inorganic molecule, like carbon dioxide. Carbon dioxide, there's no hydrogens in carbon dioxide, so it's an inorganic molecule, even though it's something that we make, being an organic organism that we are. Okay, so we're going to talk about some of these different inorganic molecules first. Okay, we talked a little bit about water. We said that water was set up with two covalent bonds. We got the two hydrogen atoms and the oxygen atom. And this first picture on the right, it shows you that the electrons are being shared with the hydrogen. And it shows you that the oxygen is a bigger atom, so that those electrons are going to spend more time around the oxygen atom. Therefore, it's going to have a little bit of a negative charge on it. Okay, and we can see that down at the bottom or right beside it, a little bit of a negative charge on the oxygen, where the hydrogen has a little bit of a positive charge. And because of that, water likes water. Okay, water likes anything with a charge on it. And since water has both charges, water likes water. Okay, so look at the bottom right picture here. Notice that because water likes water, we are able to have this molecule here form hydrogen bonds with this molecule, with this molecule, with this molecule up here, with this molecule up here. Lots of different bonds. Now they're weak bonds, But the cumulative effect of all of these guys wanting to bond to each other because of the charge means water has surface tension. Things can walk across the surface of water. Now I can't, but I see these little spiders that as long, and I can see boats that as long as the surface area is big enough because of this hydrogen bonding, I can float, these ships can float. Okay? So having water in our bodies does a tremendous service to us. Okay? Without enough water, we can't do the chemical reactions that we need to do. So there is homeostasis with respect to the amount of water that we have to have in our bodies. Okay? When we start losing too much water, that changes the concentration of things that are inside of the water that's in our body. When that gets too much, that can be lethal to us. And we'll talk about dehydration and things like that of the body and what it actually does. Okay? So some of these properties of water. Water is the best at dissolving things. Okay? Water has the ability to dissolve things like salt. Okay? It can form ions in it. So the solubility of water is incredible. Okay? We've already said that water can break bonds and make bonds, so it's reactive. Okay? It takes a lot of energy to change the temperature of water. So it has a high heat capacity. Now, how does that help us? Well, if we're having to stay at 98.6 degrees and water has a high heat capacity, does that mean it's going to be hard for us to change temperatures? Yeah, it's going to help that. Okay? And we're going to use water as a lubricant in our bodies. All the joints, we're going to put little fluid-filled sacs around the major joints in our bodies. We're going to use it to move things in the body, to protect things. Okay? So when we think about this, our body is about 2/3 water. Okay? It plays a structural role as far as hydrating our cells and a functional role. Okay? Meaning we can do chemistry in this water. Okay? And it has tremendous properties that allow us to exist because we are mostly water. Okay? Water likes itself and likes anything with a charge on it. So that causes us to have cohesion and adhesion and surface tension that I'll talk about coming up. We've said it has a high specific heat, meaning it takes a lot of energy to heat up the water. Okay? It has a high heat of vaporization. It can exist in 3 different forms on our planet. Water. Okay? Great solvent. Anything that has a charge on it, water likes, and water wants to dilute it. It wants to separate it. Okay? And the density of water. When water is a liquid, it's densest at 4 degrees. Okay? At 4 degrees, water's densest, which means even ice is not as dense as 4-degree water. That means ice floats and cold water sinks. That's the reason our lakes don't freeze solid. Okay? So it's tremendous. Okay. This slide shows us how we are able to keep things in solution once we add things to water. Okay? This shows you the water molecule with its slightly positive hydrogen atoms and the slightly negative oxygen. Okay? And it shows you when we put salt in the water that water forms hydration spheres. Water actually is attracted to the sodium. Okay, now what part is attracted to the sodium? Well, that's the oxygen is attracted to the positively charged sodium. What's attracted to the chloride is the negatively chloride is the hydrogen atoms that are positively charged. Okay, so oxygen is attracted to the oxygen of the water, I should say, is attracted to the sodium. The positively charged hydrogen is attracted to the negatively charged chloride. And it forms these hydration spheres and makes it hard for sodium and chloride to get together. So these ions stay in solution. Okay, they keep them in solution, meaning they don't come together and fall out of solution. And we end up with a bunch of salt down at the bottom. Okay, it's not the way it works. So when we add ionically bonded molecules to water, water disrupts that bond. Okay, it gets in between that ionic bond and it separates, and it causes these molecules, okay, to dissolve and stay in solution. So if we have sodium chloride, we put that in, and it's going to release sodium and chloride ions. We go from having salt to having sodium and chloride now. If it's potassium chloride, we end up with having potassium and chloride. We do whatever we want to with the chloride now. It's not bound to the potassium. Calcium phosphate, okay? And this is a good example. Notice that there's a 2, okay? A 2 outside, 2 plus. What does that mean? Well, that means 2 electrons have been donated, right? Not just 1. In order to make it happen, we had to give away 2 electrons. But calcium, now we've got calcium in the water. Okay, we can build whatever we want to out of that calcium molecule. Okay, so all of these on the left, when you put them in water, they dissociate, they separate, and they remain separated in the water, as long as there's enough water to keep them separated. Okay, so some molecules like water, others don't like water. Okay, if you react with water, you're water loving, we call you hydrophilic. If you don't like water, we call it hydrophobic. Okay, hydrophobic, and that's an old term for what rabies used to be called, because when you have rabies, you have a fear of water. So hydrophobic means a fear of water. So what things don't like water? Well, things that don't have a charge. Okay, things that don't ionize, because water wants you to have a charge on it. Okay, so we're going to be spending a lot of time talking about how much of the stuff is in the water. Okay, how much salt's in the water, how much glucose is in the water. Okay, how much vitamins do you have in the water? So we're going to be talking about concentrations of things. All it is how much stuff do you have in the water. The stuff is called the solute. The fluid is called the solvent. So for most of the time, our solvent is going to be water. Okay, so we're going to talk about a lot of things that we have to stay in homeostasis with respect to concentration. Okay, and we'll talk about it in either milligrams per milliliter or moles per liter. Okay. One of the things that we're going to keep track of is the pH. Okay, we'll have our blood pH that we'll talk about a lot. We can have the pH of the cerebral spinal fluid that we have to deal with. Okay, even pHs of certain foods that come into our body can be very acidic or very basic. And we have to maintain that level that the body requires, okay, based on this pH. What is pH? It is the concentration. Again, we just talked about concentrations. How many hydrogen ions you have in the fluid, okay? And hydrogen ion is one that has given away its electrons, so it is just a proton basically floating around. So how many protons you got out there floating around by themselves, okay? Now, if you are even, like pure water has the same number of hydrogen ions as it does hydroxide ions because it's water, H plus and OH minus, okay? So pure water doesn't have anything in it but water. It is considered neutral, and the neutral pH is 7. Okay, and from 7 we can go either way. We can either start adding more hydrogen ions or taking away hydrogen ions. Okay, if we add more hydrogen ions, increase the concentration of hydrogen ions, it becomes an acid and the numbers get lower. Okay, If we increase the amount of hydroxide ions, get rid of more of the hydrogen ions and add more hydroxide, the OH, that causes it to become more basic and the numbers get higher. Okay, so 7 is neutral. If we look at the graph here, neutral, that's right in the middle, and that's what pure water sits at. If we go this way, we're going more acidic and the numbers are getting lower. If we go this way, the numbers are getting higher, we're getting more basic. Okay, and it shows you things like here's our blood, just a little bit more basic, okay, but beer, vinegar, wine, and pickles, it's pretty acidic. And we're going to put that into our bodies, so we have to have a way to make sure that we don't have too much acid, okay, change our blood. Because if we get too acidic, it can damage cells, change the shape of our proteins, and interfere with our normal bodily functions, those physiological functions that we have in the body. Okay, so this is something that they always ask on those tests. You get a pH question to make sure you understand how pH is set up, where you're getting more acidic if the numbers go down, you get more basic if the numbers go up. Okay, and we'll talk a lot about pH. Okay, there's things in the body that can cause us to have a low pH, become more acidic. Those things are termed as acidosis. Okay, there are also things that can make us go basic. We call those alkalosis. Okay, and we have things inside the body to help us control this pH. Okay, we have buffers that allow us to produce salts from this. Okay, so if you take hydrochloric acid, which is the strongest acid, HCl, and you add it to the biggest base we have, the most caustic base we have, sodium hydroxide. This hydrogen and this OH group come together, and that makes water. And the sodium and the chloride come together, and that makes salt. Okay? So, when we try to neutralize a very acidic substance or a very basic substance, we use the opposite to neutralize it, because what we end up forming is water and salt. Okay? Water and salt, and that allows us to neutralize this by buffering them. Okay? In the water, we also have dissolved gases. Okay? And for living things, we have 3 main gases that we will look at. That's oxygen, carbon dioxide, and nitrogen. Now, we got to have oxygen in order to run our mitochondria. And we've got a whole set of blood cells, hemoglobin, red blood cells, okay, with the hemoglobin protein inside of them to move around oxygen to make sure we get enough oxygen. And then once we utilize that oxygen, we create a waste product that's called carbon dioxide. And that carbon dioxide we're going to get rid of, okay? The nitrogen, it is very abundant. Most of our atmospheric gas is nitrogen, but we can't use it directly through respiration when we do the breathing, okay? We have to get our nitrogen after the plants have dealt with it, okay? And we'll talk about both of those. But we can find oxygen, carbon dioxide, and nitrogen floating around in the fluids of our body, okay? Okay, all of those that we have just discussed were inorganic molecules, okay? We talked about water, okay? We talked about acids and bases and salts, and we talked about dissolved gases, okay? Of that, water is very, very important, okay? What we have left to talk about are these organic molecules, and there's 5 different groups of organic molecules that we're going to talk about. Those are carbohydrates, lipids, proteins, nucleic acids, and high energy compounds, okay? Now, all of these are necessary for us to take in our bodies, and we get these through the nutrients that we eat, okay? That old saying, you are what you eat, is completely true, okay? all of the structures that we have built in our bodies have come from the foods, have come from these molecules that we've put into our mouth and moved across that tube into our bodies. Okay? So let's talk about these different organic compounds and we'll be done with chemistry. Okay? So to do this, we can look at some functional groups that stick off of it. I'll try to draw your attention to these as we go through them. There is a C double bond to an O to an OH, so that's carbon, double bonded to an oxygen, and then it's single bonded to an oxygen that is bound to a hydrogen. We call that our carboxyl group. Okay, and we see it on fatty acids and amino acids. We have an amine group. This one has a nitrogen in it, so it's easy to identify. A nitrogen with two hydrogens, and we're going to see these in our amino acids that make up our proteins. We have a hydroxyl group, just an O bound to an H. Okay, and then we have this phosphate group. It is the one with the phosphate with 4 oxygens around the outside of it. Okay, so when we see these, we know what kind of molecules we can be dealing with. The first one, let's talk about carbohydrates. Okay, carbohydrates, things like simple sugars. Okay, and we can go from a simple sugar, putting a couple of simple sugars together and making a disaccharide. From disaccharides, we can put several of these sugars together and make polysaccharides, things like starches and glycogen and things like that. Okay, so the way that we store the sugars in our body is by producing something called glycogen. Okay, that's our source of sugar that we need. If the zombie apocalypse happens and we have to run for our lives, we're going to release a bunch of glucose, put the glucose into our bloodstream, carry it all over our body, and allow us to run away. Okay? So, carbohydrates are known as our quick energy sources. Okay? We also find them on our membranes that make the cells membranes sticky, but we use these as our favorite source of energy because we can burn it very quickly and generate a bunch of ATP from it. Okay? Lipids. Okay? Lipids or fats. Okay? These are hydrophobic, which means water doesn't like. Fats and oils, we know oil and water doesn't mix. And it's mostly carbons and hydrogens here, just like our carbohydrate was a minute ago. And we're able to use it as a storage molecule for extra energy. Okay, it's also important in making things like our steroid molecules, steroid hormones, cholesterol that we need in our cells, things like that. So this shows you a fatty acid. This is one of the lipids. And look at all these carbons and hydrogens down here at this bottom. Okay, there's tons of carbons and hydrogens. Here's glycerides. These are fatty acids. Again, look at all of these carbons and hydrogens that we see. Just a few oxygens. Okay? So, these are the reasons why it does not like water, because these don't have a charge on them. Okay? They don't have a charge on it. Water doesn't like it, so water pushes it away. So what happens to my oil and vinegar salad dressing? All the oil ends up on the top because it's pushed away. Okay? But we got to have these. Even these steroid molecules we'll talk about being a lipid. Okay? Estrogen, testosterone. Okay? Cholesterol. All of these, we got to have a special way to carry them in the body because water doesn't like them. And we don't want these to all stick together like the oil and vinegar dressing does in our bodies. Okay? This is probably the most important molecule for us when we go to talk about the cell. It's called a phospholipid molecule. Okay? It has all those carbons and hydrogens down here at the bottom where the two tails are. That makes it hydrophobic. But up here, you get a non-lipid group up here that is hydrophilic, which likes water. So this part likes water. This part doesn't like water. And that's going to be able for us to use it as a boundary to maintain the cell's membrane. Okay? And I'll point it out to you in the next chapter. Okay, third one, proteins. Okay, first sentence, proteins are the most abundant and important organic molecules. It's got carbons, it's got hydrogens, it's got oxygen, and now we're going to add nitrogen to it. We're going to add a nitrogen to it. So it's easy to find these. We're looking for the nitrogen. And we're going to use 20 different amino acids to make up these proteins. We call these 20 different amino acids, okay, are building blocks. These are the Legos for making the proteins. And proteins, because they are the most important up here, look at some of the functions here. Structural proteins, contractile proteins, transport proteins. They're going to help us regulate our pH. All enzymes are proteins that set our metabolism. All the chemical reactions in our body. Hormones are proteins. Even the antibodies are proteins. Okay? So we make tons and tons of proteins in our body. We're going to talk about these over and over and over again. In fact, in the next chapter, we're going to talk about how we make proteins. Okay? It's critical that we understand how we make proteins. If that's how we're going to make antibodies, if that's how we're going to make enzymes, if that's how we're going to make hormones, if that's how we're going to make the structural things that make up our cells, got to know how to make these proteins. Okay? So here's what the amino acid looks like. There's always this central carbon in the middle. Okay, that's this white one that you can see here, central carbon. And on one side, there's a carboxylic acid group. On the other side, there is an amino group. That's the nitrogen group. Okay? There's always a hydrogen attached. And then there is this R group. And this R group can be 20 different things, because that's what the amino acid looks like. They all have these three, and this is the part that's different. Okay? So we're going to have 20 different R's when we look at these amino acids. So if we look at this, this shows you glycine as an amino acid, central carbon, carboxylic acid group, amino group, hydrogen, and what's its R group? Well, its R group is just hydrogen. Here's a different amino acid. This one's alanine. Here's central carbon, carboxylic acid group, amino group, hydrogen group, and what's its R group? It's a CH3. It's a methyl group. Okay? So two different ones. We can see that this is the only part that's different. Okay? And we've got 20 different ones. And you don't have to memorize them at all. Okay? But when we put them together, okay, we use our old buddy water to do it. Okay? Notice that when you line them up, as we see up here, it ends up that the hydrogen and the OH group are side by side. Can we get rid of that? Can we make water out of this? Absolutely. And when we do, there's a bond here we have to deal with and a bond here that we have to deal with. So we're going to bond the nitrogen to the carbon, and that's called a peptide bond. And what we did was we got rid of the water. That's called dehydration synthesis. And we created now two amino acids stuck together. Okay? We formed a different molecule. We've done some chemistry. Okay? If we want to break it, all we got to do is add water to it, and water is going to take us back to this form. Okay? So it's not going to be hard to make these proteins. We just got to put them in the right order. And we got all kinds of shapes for these proteins. Okay? These first two show us structural proteins. Okay? If it's a long line of them, like a train, where all the amino acids make up one of the cars on the train, okay, we call it a primary structure. It's the polypeptide chain. Okay? If we take this polypeptide chain, we take this thing up here, and we coil it, or we flip it back on.
Yeah.
Okay, so we go this way.
That's fine, it's almost done.
Run it back this way, and then run it back this way. We make a sheet. These are both structural, meaning these are going to have a function in the body to be a structure for us. Okay, so things like this would be like a 2x4. Okay. Okay, or a protein fiber or something like this. This could be a wall that we use in the cell, or we're making an organelle or something like that. Okay, this could be some of the fibers that we see in the cell that are larger, that are going to give it its shape and things like that. Okay, so these are just amino acids stuck together, but we're going to put them in different shapes to give us the different functions of these proteins. So these first two, like I said, are structural proteins. The next two, these are functional proteins, meaning they have a unique shape. Notice we've taken that coil and we've just wadded it up on itself. Okay, it's globular, we would say. And then in the one down here, quaternary structure, tertiary structure, it's flopped down onto itself and wadded up. Then we have this one where we've added 1, 2, 3, 4 of these globs together. Okay, this is what hemoglobin looks like inside of our red blood cells. This is the protein. Okay, if you get it wrong, we're not able to carry oxygen. Over here, here's keratin or collagen. Okay, notice we've got 3 different coiled structural proteins that are going to give us this big structural protein. It's going to be like a column in a building or something like that, but for our cell. Okay, so we say that the tertiary and the quaternary structure have unique shapes. They're globular, which means they are for binding things. If you are long and rigid like this, you're a structural protein, and you're there to be a structure. Okay, so you're going to hear me say this 1,000 times. The shape of the protein dictates its function. Okay, the protein's function is all about its shape. Change the shape, we change the function. Okay, and the shape is determined by the sequence of amino acids. 20 different amino acids. Okay, and we're going to put them in all different combinations, and that gives us different shapes because we've got all these different R groups sticking off. Okay, we can denature the protein if we add heat or pH to it. Okay, so imagine, okay, y'all know the whites of the egg. Okay, when you break an egg, it's that clear, you're going to fry an egg, that clear part is all protein. It's called albumin. Okay, what happens when you heat up that clear part? It changes color, turns white. We've changed the protein structure of it. Okay, I do the same thing if I make ceviche, okay, which is fish that you cook in lime juice. The lime juice is very acidic. It changes the color from that opaque fish color to the nice white cooked fish color. Okay, so fibrous proteins are structural. Globular proteins are going to bind things. They're going to have an active function. One of the most important of our proteins are the enzymes. And these enzymes facilitate chemical reactions. They make chemical reactions go faster because they're going to cause the two things we're trying to get together to be in close approximation with one another. Okay? They're going to be right beside each other. So if this one binds here and this one binds here, they're together, it's real easy to hook them up. And we make the product, and look, we got the enzyme back to keep doing it again. Okay, so if you have an enzyme for something, it's like I said, it's like having a coupon for it. Okay, doesn't cost you as much energy, okay, to get these two together. If you've got an enzyme, we're going to be able to make them a lot faster. Okay, and this just shows you if I don't have an enzyme, this is how much energy it takes to do it. If I do have an enzyme, it only takes this amount. So it's much better if we've got an enzyme. And we'll talk a lot about enzymes, y'all. There's hundreds of enzymes we're going to learn. Okay? All right. When we're talking about these, there's different kinds of enzymes. We'll talk about cofactors, coenzymes, and isozymes. Okay? But when we're looking at their characteristics, it's always one enzyme has one reaction that catalyzes. Okay? One enzyme catalyzes one reaction, and they only work at a specific rate. They can't go, you can't make them work even faster if there's a whole bunch for it to do. They only work at a specific rate. And we have the ability to turn these on and turn these off. As we go through the development process, we're able to turn on certain enzymes and turn off ones that we don't need anymore. Okay? I worked on bears when I was in graduate school, and bears have two different sets of enzymes. They have a set of enzymes that works at their normal temperature, and when they go crawl in the cave for the winter, they have a different set of enzymes that work better at cold temperatures. Okay, so we'll talk about these. All right, our next one, nucleic acids. Okay, this is our genetic material. This is what we're going to hold the information for making all the things that we make inside of us. Okay, these are large organic storage molecules for the genetic information. Okay, DNA and RNA. DNA is deoxyribonucleic acid. We get it from our parents. It determines what we're going to look like on the outside, how we're going to work on the inside. It's going to control our protein synthesis, our enzyme production, and our metabolism. Okay? And the nice thing is you can always, if something doesn't work right, you can blame your parents for it because they're the ones that gave you your DNA. Okay? And then we've got an intermediate that we'll talk about, and we'll talk about this one with certain kinds of viruses where they are RNA viruses. And it's just an intermediate in the process of making the protein. Okay? When we look at DNA, there are 4 nitrogenous bases. Notice that there are nitrogen groups in each one of these, so we call it nitrogenous bases. A's and T's and G's and C's. That's adenine and guanine and cytosine and thymine. Those are the ones that are found in DNA. In RNA, we do not have thymine. We replace thymine with uracil. Okay, so DNA's bases, A's and G's and C's and T's. RNA's bases, A's and G's and C's and U's. Okay, and they link together to form a double-stranded DNA molecule. Okay, the individual units that make up our DNA are called nucleotides. They are a phosphate, a sugar, and the nitrogenous base. The phosphate and the sugar make up the backbone of it. That's this kind of tan part that goes around this way and this way. And the sugar, the nitrogenous bases are what bind together in the center to hold it together, forming double-stranded DNA. Okay, the last molecules that we have to talk about, these last organic molecule group is called our high energy compounds, ADP and ATP. And these are related to one another. ADP has 2 phosphates. So I'm going to circle that ADP for you. It's right here. Okay, it has adenine, a ribose sugar, and 2 phosphates. Okay, to make ATP, all you do is add a phosphate to it. Okay, so this whole thing is ATP. So ATP is available energy. Okay, it is energy that we can utilize because we've put this high energy bond right here. And when we break this high energy bond, pow, it liberates energy. We get energy from that. We also get ADP separated from a P. So we say we got ADP and P. What is ADP and P? That's used up energy. How do we make more energy? We'll put the phosphate group back onto the ADP, and now we've got ATP. What's it going to take? Well, something that can generate a high energy bond for us. We can do that if we eat a bunch of carbohydrates. We can have enough energy to put a bunch of phosphates onto ADP and make us a bunch of ATP. We call it phosphorylation. Mitochondria is going to do that for us. Okay, enzymes are going to help with that. So we're going to talk about ATP and ADP a lot when we get to the muscles, when we get to the nervous system. Okay, anytime we're generating energy and using that energy. So that's the chemistry. Okay, that's the chemistry.